All right. So moving on through chapter 1 here. Continuing on with functions. So starting off here, kick off, what is function notation? Well, function notation is that f of x. So really what it is that way to identify which equation you're working with. A lot of times we'll be dealing with multiple equations going on. So f of x may be one, g of x may be another, h of x is another one. That's when we know, hey, we're talking about that one when we do f of 2. We know, hey, we got to put 2 in for that function. Now, continuing on, next thing we're going to hit is the difference quotient. Difference quotient is the expression f of x plus h minus f of x all over h as long as h is not 0. Now, where this thing builds towards, especially if you take calculus next year, is we use this quite a bit in calculus. Now, in here in advanced math, we don't hit it a whole lot, but we give you that little bit of taste so that it's easier when you get to calculus. So, first thing we do is, if this is our function, f of 2x squared minus x plus 3, is we have to do the f of x plus h part. So, remember, that entails everything that's inside the parentheses replaces the x. So the 2x squared becomes 2x plus h squared. Minus x becomes minus x plus h, and then plus 3. Now, this here has to get FOILed out. Just don't distribute the square. So x plus h times x plus h. So x and x would be x squared. X times h would be plus xh. H times x would be plus xh. And h and h would be plus h squared. So what we have here is two parentheses. X squared, we have 2x plus h's plus h squared minus x plus h plus 3. So I'll make a little divider so we know that's separate. So we have to distribute our 2 in. So this becomes 2x squared plus 4xh plus 2h squared. The negative would get distributed, minus x minus h plus 3. Now, that's as simplified as we can make it. There's no other terms we can put together. But that's the more complicated part of the difference quotient, is just finding that f of x plus h. From there, then, we can finish solving this out. So, we said the f of x plus h was 2x squared plus 4xh plus 2h squared minus x minus h, minus the original, which is 2x squared minus x plus 3. So the minus f of x means minus your original equation, and then we put it all over h. Now, first thing we're going to do is we're going to distribute this negative through. So what we're going to end up having is 2x squared plus 4xh plus 2h squared minus x minus h. Oh, and we forgot the plus 3 in here. Plus 3 minus 2x squared, minus and minus would be a plus x, and then a minus 3, all over h. So, gets to be a lot, but now we can start reducing. So, key here is everything that doesn't have an h should cancel out. If it doesn't, we have to go back and check our math. So, I have a positive 2x squared and a negative 2x squared. Plus x minus 3 plus 3. So the only thing I have left is 4xh plus 2h squared minus h all over h. I'm kind of running out of room here. From here, we can reduce everything by an h. So when we do that, we get 4x, because this h canceled, plus 2h, because it was h squared, so one of them can cancel. And this h back here becomes a minus 1. And that would be your answer. Now, the next thing we're going to talk about is piecewise functions. So piecewise function, basically we're going to have multiple equations going on at the same time, and that domain we'll have selected will use certain equations at certain times. So like here, if I did f of, say, 30, well, 30 fits between 0 and 60. So I would do the top function and I would get 20 out. Same thing if I did f of, say, 45. Because again, fits in here, so you get 20. Now, once I hit f of 60, well, 60 still is in this because it's an equal, so it would be in this top one, and we would get 20. But as soon as I go to f of 61, well, now I have to put it into this equation, and I would do 20 plus 0.4, 61 minus 60, which would be 1. So 1 times 0.4, and we would get 20.4 for an answer. So that's what this does. This is saying, hey, for these t's, we use this one. For these t's, we use this one. If it doesn't fit those, like say we get a negative t, well, there is no domain for that, so we can't use it. There's nowhere to put that. So it's just from 0 to basically 0 to infinity that we can do with this one. Now that graph is going to follow each for its desired domain. So on that graph, we would start and you would see this. You would see that flat line because they're always 20. Once we hit that 60 mark, then it's going to start sloping up. So it'd be something like that. Now, when it comes to graphs, constant means there's no change in the range of the domain changes. So think you're going to have a flat line on the graph. So it's not going up, it's not going down, it's just staying constant. Decreasing. Again, we're going from left to right. So as we go that way, you're going to see it working downward if it's decreasing. And increasing, you're going to see it working upward as you go from left to right. So, if I draw you a graph here, so let's say here's our max at -1, 2. Here's where we minimize at, say, 2, -3. And at this point is where we stop and we start going back up, which would be at, let's say, 5, -3. Well, looking at this, starting with increasing. Well, we always go from left to right. So as we're coming across, what are we doing? Well, as we're coming across, we're working our way up until we hit that max. So working our way up, so from -infinity until -1, and we use a parenthesis. So it's up until that point, because at that point we're not increasing anymore, we're not doing anything. But until we reach that, we're working our way up. Now, from there then, we're now decreasing until we get to this point. So we would say, well, from 2 to 2, or -1, sorry. So, good example here. It's only the x's we look at. So from this x, -1, until this x of 2, we're decreasing. Well, where are we constant? Well, where do we have the flat line? Well, right in between these 2 points. So from 2 to 5. Now, once we hit to 5, well, now we're going back up again. So that would fall under increasing. So you'd put the u and be a parenthesis 5 to infinity. That's how we'd answer this one. So from the 5 mark until infinity, we're going to keep going up. So if there's multiple things, separate them with a u, which means union. So this one and this one. All right. Now, we have some relative maximums and relative minimums. This here, -1, 2, would be a relative maximum because in this area, it's the high point. It's not the overall high because over here we're going higher. But in this area, it's a high point. Same thing with the minimum. If there was a spot where we're going like here, say for example, if this curved back up right away, this would be the minimum. Well, it's the relative minimum because this is going out further, so it can't be the absolute minimum. Now, as far as even and odd goes, so a function is going to be even for all x in the domain of f of negative x equals f of x. So what this is saying is this. If we have even exponents all the way across, generally that will be even. A constant is always treated as an even. So what that does is if they're even exponents, if you put a negative x in, it won't change the sign. Because if it's multiplied an even amount of times, it's going to be positive. So think about it as this. If we put a negative x in, and we would get the exact same thing out, mainly because we have even exponents, that would make it even. Odd, same idea. So odd exponents for this one. So reason why that is. So here we're going to get the exact opposite out from where we started. So we need them to be odd exponents so that we have an odd amount of times you're multiplying, which makes it switch the sign so that we get the opposite. Now, if some of it changes, some of it doesn't, so some of them are even, some of them are odd, it's going to be neither. So looking at this, technically this is to the first, so we would have x to the third, x to the first, which makes this odd since both of those are odd. X to the fourth, x squared, both even, so even. I have an x squared, an x, and a constant. Constants are always evens, but 2x is really x to the first, and therefore makes this a neither. So if you have some even, some odd exponents, it's for sure going to be neither. Now, as far as graphs go, the graph of an even function is going to be symmetric with respect to the y-axis. So if I drew this out, if I flip it across the x-axis here, the graph would match up on either side. So that's y symmetry for an even function. And again, this is like x to squared, x to the fourth, x to the 20th, yada yada. Even exponent for all the terms, not just the lead one, but for all the terms. The lead of each one totally forgot where I was going with that. So the graph of an even function symmetric with respect to the y. Right. So whether it's squared, fourth, 20th, as long as it's even, it's going to be a parabola. That's what I was trying to say. Sorry, lost my train of focus here. Anyways, oh, that's where I was going. So the lead, so on an exponent, whatever that lead is generally what this is going to be, too. So if the leading one is x squared or x to the fourth, x 20, if it's even, it's going to look like this, which is something we'll get into more, I believe, the next chapter, that leading coefficient, or not leading, yeah, leading coefficient test. And we'll get into all that stuff. But if we're odd, going to look like that. So like x to the third, x to the fifth, x to the 37th. It works. Now, if it's just y equals x, that's a straight line. So an even function will look something like this, where both ends are going up. Odd will look like this, where one's going up, one's going down. And then, if you think about it, if it's x to the first, it's still odd, so that's why one's going up on one side, one's going down on the other. But it's a straight line is the difference. These other ones, when you get above x to the first, so x squared starts it technically. You're going to get curves instead of straight lines. Now, one thing we haven't hit yet are called step functions. So step functions in which a graph resembles a set of stairs. So one of those is the greatest integer function, where it's written as int of x, or just in brackets x, which means the greatest integer that is less than whatever number we have. So by stair steps, I mean this. So we'd have a solid slide open, solid slide open, solid slide open. So they look something like that when you graph them. So the greatest integer function would be like if I had 3.9. Well, the biggest integer not bigger than this, so the biggest integer that's less than it, would still be 3. Just like if we did, say, the greatest integer of 3.1. Again, anything really in between here is going to go to 3, because the biggest integer not bigger than it. Well, an integer is a whole number. 3 point, not a whole number, so the next one lower than it would be 3. So that's how we're getting that. And that's it. That's it for this lesson. Please let me know if you have any questions, comments, concerns. You can email me, pan me, send me a message on Google Classroom. Remember, you can always pause if you need time to write stuff down, or you can rewind it and hear something again if you need to. Please, they're all there for you to use. Always, until next time, we'll talk to you later.